All right. Hello again. Welcome to Recitation 7 on Mechanics and Materials 1. We also have 4 questions to go through. This is the first one. So the stress-strain diagram for a bone is given in the picture. So stress versus strain. Usually you are, let's say you are expecting a linear curve here, but this is a polynomial of order 3. And this polynomial, in particular, pay attention, it expresses strain in terms of stress. Okay? Stress is your y-axis, epsilon or strain is your x-axis. So this is kind of different from what you usually expect from a graph. Okay, so it's not something like y equals f of x. Okay, so this is the opposite. This is x equals f of y. All right. And then for this particular example, let's say sigma is in kilopascal. You are asked to determine the yield strength assuming a 0.3% offset. Okay, what does that mean? That means if you have the module of elasticity, so let's say if this thing was linear, right? At the beginning it's linear, right? So you would have this line, this is at the beginning. Okay, let me just draw it better. So this is your straight line. And that angle that we have there, at the very beginning, this point is very important. This is the point where stress and strain are both 0. Okay, so epsilon is 0, sigma is 0. And obviously, we discussed about this. If you have like a linear elasticity, loading, unloading, you always go up and down this. Okay, now, the question basically tells you, if you have a point that has your yield stress, let's say your yield stress is here, yeah. So this is your yield stress. If you draw your elastic curve from that point, you know, if you draw this one from that point, you get 0.3% in your strain axis. Okay, so this distance is 0.3%. All right? Now let's call this angle maybe theta for simplicity. And then your module of elasticity, E, usually, or your Young's modulus, in a extension test is simply tangent of that theta. Okay, now, how do we calculate this? We need to calculate basically the stress-strain relationship at the very beginning. So you would, in a usual linear case, by the way, sigma is equal E epsilon, right? Or equivalently, you can think that E is equal sigma divided by epsilon. Now, if it is nonlinear, it would be the same thing, but it's incremental. Okay, so E would be d sigma with respect to d epsilon. Does that make sense? But then you want this relation, d sigma over d epsilon, only at the very beginning. So that is the point where epsilon is 0. Or respectively, stress is 0. Okay, so I'm talking about this line. Once we have this line, once we have the slope of this line, all you need to do is to write the equation of this line and intersect it with the curve, okay? So that's what we want to do. We want to find the equation of this line and intersect it with the curve to find this point, which is respectively your yield stress. But then again, in order to have the equation of this line, I mean, we know where it starts, we have the offset, it's given, but we don't know what is the slope. The slope itself, we need to calculate it from, from that linear relationship. Okay, so everything is good. We can just do it. There is only one little problem here, that you don't have a relationship between stress and strain. If you had this would be a very simple example, because then this would be simply your sigma prime. But you don't have it. You have actually the inverse of that relation. You have strain in terms of stress. Okay? That's the only tricky part, but it's not too tricky anyway. So basically what you need to do is to kind of invert this thing. So you would say d sigma over d epsilon, let's say at that epsilon 0, is basically d epsilon over d sigma, well, also at the same point, but also where sigma is 0, to the power of -1, or inverse of it, right? So you need to invert the sigma over the epsilon to get the epsilon over the sigma. Now, this is easy because you have epsilon as a function of sigma and you can calculate it. So epsilon is 0.45 10 - 6 sigma plus 0.36 10 - 12 sigma cubed. That means the derivative of epsilon with respect to sigma is 0.45 10 - 6 plus 3 times 36 is 108, so that's 108 10 - 12 sigma squared. Okay, now at epsilon 0 or at sigma 0, at this point, this will be 0. So this would be your E, basically. This is, this is your d epsilon over d sigma. In the inverse of it would be E. Okay, so therefore, the epsilon over the sigma at, at epsilon 0 would be 0.45 10 - 6. Now, you just invert it. You get E, which is 2.22 times 10 to 6, right? So 1 over 0.45 is, let's say, 2.2 or 2.22. Then 1 over 10 - 6 is 10 to the power 6. But remember, stress is given in kilopascal. So I'm going to also incorporate that and write this simply as gigapascal altogether. All right? You can write it as, again, times 10 to the power 3 megapascal, but okay, so that's that. Does that make sense? Okay, so that's our module of elasticity, or Young's modulus. Now that you have that, all you need to do is to write the equation of this line. Now, what is the equation of that line? It's actually pretty simple. The equation of that line is simply this. Sigma is E times epsilon minus 0.003. Right? So that's the equation of that line. And all you have to do is to set these two equal and to intersect them. Now you know what is E. E is 2.2 times, let's say, 10 to the power 9. All right? And epsilon is here. So you can basically set the epsilons equal and calculate sigma. That's what we want to do. So this relation if you write it in terms of epsilon, or if you take epsilon out, it would be, let's say, sigma divided by E plus 0.003. This is epsilon, right? Now, this should be that cubic polynomial equation, 0.45, 10 minus 6, sigma plus 0.36, 10 minus 12, sigma cubed. All right? Now it's easy. So if you just look at this equation, you basically have one equation in terms of sigma, and you can just solve it for sigma, and the sigma that you get is the yield stress that you are looking for. So if you do it, you get sigma as 2. Okay, let me just write it like this. So 2030 kilopascal, because sigma is given in kilopascal, or you can just say it's 2.03 megapascal. That would be your yield stress. Do you have any question? All right. So that's the first exercise. The second one is very interesting, sort of combining different concepts that we learned. You have a little test specimen alloys, or aluminum alloys for testing here, shown in the figure, which has the length of 50 millimeters. So this is 50 millimeters. A cross section is, let's say, it's circular, and it has the diameter of 12.5 millimeters. Okay, you apply extension to this with a load of 40 kilonewton. So the load you want to apply is 40 kilonewton. Now, usually we tell you if this is the load, and then calculate how much you get in length change or longitudinal strain. But in this example particularly, it doesn't ask you about longitudinal strain or change of length. It asks you about the change of diameter, or actually the new diameter of the specimen, which is in the other direction. So this is a very nice example to sort of introduce the Poisson ratio into the picture. Okay? So basically what we want to do is the following. We are looking for the new diameter. Let's call it D prime. D prime is the old diameter plus the change in diameter. Now, the old diameter is 12.5 millimeters. What we need to calculate is the change of diameter, right? Now, how do you calculate the change of diameter? You need the lateral strain, right? So delta D itself would be lateral strain times D. Does that make sense? Or remember, basically, strain is delta D divided by D, or lateral strain is that anyway, right? Now, but then you don't know what is, so this is again 12.5, so we know that. But then we don't know what is lateral strain itself. So we need something for the lateral strain. Now, lateral strain is related to longitudinal strain via Poisson ratio. So that's minus Poisson ratio times longitudinal strain. Okay, remember, Poisson ratio definition is minus epsilon lateral divided by epsilon longitudinal, right? So basically, epsilon lateral is minus Poisson ratio times epsilon longitudinal. Now, we don't know any of this, and we need to calculate them. if we calculate them, then we get epsilon lateral, we put it here, we get delta D, we put it here, we get new diameter that we want. So this is like a very nice stepwise problem. So how do we calculate Poisson ratio? For this example, we know what is the shear modulus. It's 27 gigapascal. So we need to find Poisson ratio from G and E. So if we know G and we know E, remember, from every pair of material parameters, you can compute the remaining ones. And for Poisson ratio, if you want to remember that, you remember our relationship between, let's say, G and E. It was G equals E divided 2 times 1 plus nu, okay? Which essentially gives you Poisson ratio equals E minus 2G divided by 2G. Okay, or let's maybe write it in this. E divided by 2G minus 1. Okay? Now, if we know E and we know G, then we can calculate Poisson ratio. G is given, that's 27 gigapascal for this particular aluminum alloy. What is E? How do we find E? We don't know E, but we have this very nice linear graph, right? So again, E is simply sigma divided by a strain on that particular graph. So from this, you can just calculate E equals sigma divided by epsilon, or sigma equals E epsilon. Sigma is 350 megapascal, and strain is 0.0048. So that gives you E of 72.92 gigapascal. Okay, so now we know also what is E, 72.92. From that, we can calculate the Poisson ratio to be 0.35. Okay, so remember here we had two unknowns. Now we know at least what is the Poisson ratio. Poisson ratio is 0.35. The other thing we need to calculate is the longitudinal strain. Now, your longitudinal strain is the change of length divided by the initial length. So it's delta L divided by L. But also that one is the one that you get from the force you apply. Okay? So in other words, this is also your stress divided by E. Okay? But then stress here is your force divided by area. The force is the 40 kilonewton that you applied. So this is 40 kilonewton. Area is pi over 4 d squared, and then d is the same 12.5 millimeters. Okay? So as I mentioned, usually in this sort of problems, we are looking for something like this, but in this particular example, we are not even asking you for that. Okay? So you just calculate the longitudinal strain from the relationship you have. Again, from that relationship, obviously, you can calculate delta L if you wanted to. But we are not asking you about that. So the problem makes it a little more complicated. Anyway, from this, now you have 40 kilonewton, you have pi over 4 d squared. So you can calculate that stress that you apply. So stress would be 325.95 megapascal. And E, you have E already. We just calculated it. It's here. So you just divide that sigma by E, and you get your longitudinal strain that is 4.47 times 10 minus 3. All right? Okay, so let me just box this. So that is your longitudinal strain. That's your Poisson ratio. And all you have to do is to insert those into this relationship to get the lateral strain. And if you get the lateral strain, you put it on the relationship above it. To get delta D, then you put that on the relationship above it to get D prime. Okay, so if you do that, then your lateral strain would be simply, let's say, minus 0.35 times 4 times 47 times 10 minus 3, which is minus 1.5, let's say 157 10 minus 3. That's the lateral strain. And then from that, you get delta D, which is again epsilon lateral times D. And that gives you minus 0.01957 millimeters. And D prime is D plus delta D. But remember, delta D now comes with a minus sign, which makes sense because we are extending it, so it gets shortened in the other direction if Poisson ratio is positive, which it is, and that would become, let's say, 12.5 minus 0.01957. That is, let's say, 12.48 millimeters. Okay, so you lose about 0.2 millimeters. Sorry, 0.02 millimeters. Or it gets shortened that much. Does that make sense? Okay, just a simple question. What do you think if I apply 80 kilonewton instead of 40 kilonewton? So I double the force. What do you think will happen to this? So let's say here we have a shortening or reduction of 0.02 millimeters for 40 kilonewton. If we have 80 kilonewton, do we get twice that, or do we get more or less? Is the relationship is linear or quadratic? You know, there is this area here, right? That's, I think, the confusing part. So it shouldn't confuse you. That area comes only to calculate the stress. That's the initial area, right? So the initial area doesn't change in this example. If you make the force twice as large, you get a stress that is twice as large. Then you get a longitudinal strain that's twice as large, and then you get a lateral strain that's twice as large. So it means you'll just lose. Basically, you get a shortening that's twice as large. So it's a linear relationship. Does that make sense? So you shouldn't get confused by that D squared that you see up there. I think that's maybe a little confusing. All right. So that was the second question. Here is our third question of today. When the two forces of P, so we have these two forces P applied in these distances of 1 and 2 meters from A, on this, let's say on this beam, and you can imagine beam is almost rigid here. We have these two forces applied. The beam is made from steel, and then there is this rod BC at the end. When we do this, the diameter of the rod goes from 40 millimeters to 39.99 millimeters. So you get 0.01 millimeters reduction of the diameter in BC, which kind of makes sense, right? I mean, if you apply these two forces, you can imagine this is a hinge basically. So this thing is coming down and it's going to basically elongate member BC. And if the member BC gets elongated, then it would have a reduction of diameter. So the question is not super complicated really, but it wants you to compute the magnitude of each P for that to happen. This is kind of the inverse of the previous problem. All right, so what happens here is that we will have a force in this member, which that force would be, let's call it FBC. That force would be related to P, but also on the other hand, that force would be related to your stress and strain in the beam, and then you can make the connection. That's the game we need to play. So I'm going to just draw that force here. Let's say this is FBC. Now, if you write equilibrium of moments with respect to point A, you see the FBC, it has two components. It has a vertical component, it has horizontal component. The horizontal component doesn't enter into this equation, so it doesn't create a moment. The vertical component, on the other hand, would be FBC times 4/5. So if you look at this example, or this triangle, this is our famous 3, 4, 5 triangle, right? So this component of FBC would be four over 5, and the horizontal component would be 3/5. All right, so, and then this will cause a counterclockwise moment with respect to point A. So assuming that counterclockwise is plus, then you get FBC times 4/5 times 3, distance is 3 from A, minus P times 1. So this is the clockwise moment from this. The distance is 1. Then this one, the distance is 2, and then it also gives you a clockwise moment. Minus P times 2 is 0. And then from that equation, you find your relationship between the force inside the beam and P. So from that, you would connect, let's say, a strain or a stress in the beam to P, okay? Now, for this particular example, by the way, let me just write it on the side. We know the material properties. It says it is made from a particular steel that we know. So let's say Poisson ratio is 0.32, and E is 200 gigapascal. Okay, so if you need, you can use that. Now, in that member BC, therefore, stress would be FBC divided by area. FBC is 1.25 P. Area would be pi over 4. Diameter was 40 millimeters, so 0.04 squared. Okay, pi over 4d squared. So that is stress in member BC. Does that make sense? Now, on the other hand, we need to now approach the problem like we did for the previous example. We need to compute that stress from our stress-strain relationship. We know that stress, on the other hand, is also E epsilon BC. Now, epsilon in this would be basically longitudinal epsilon, right? This is what we called longitudinal epsilon. But also remember that longitudinal epsilon or let's say again, if I write Poisson's ratio, remember this is minus epsilon lateral divided by epsilon longitudinal, right? So epsilon longitudinal is minus epsilon lateral divided by Poisson ratio. Okay? So this thing itself is E times epsilon lateral divided by Poisson ratio, well, with a minus sign. Does that make sense? But epsilon lateral itself, we can now calculate it from the diameter change. Epsilon lateral is, remember, this is, let's say, D0, and then it becomes D after deformation. So it's, let's say, D minus D0 divided by D0. So D minus D0 is 39.99 minus 40 divided by 40. So epsilon lateral is minus 0.25, 10 minus 3. Okay, so we have that. We know Poisson ratio is 0.32. We know E is 200 gigapascal, right? So from all of these, we know that sigma BC is simply 156.25 megapascal. All right? So you get this from your stress-strain relationship. This is very interesting, this example. This is your stress-strain relation. Sorry. This is your stress-strain relationship. This comes from your equilibrium, okay? They all have stress in them, but stress, you know, it's now the connection between the two. So what you need to do is simply to set these stresses equal, because it's the same stress, and then you can calculate P, okay? There is only one little step that you should usually check. In this example, it's not given, so but this is our assumption, that this stress is smaller than yield stress, okay? If this stress is not smaller than yield stress, then that member cannot carry this much stress, right? And it can only carry as much as, let's say, its yield stress. Then we need to, we need to basically truncate this at that level of stress, and we need to work with that. So we will have examples in the future, and you will have such examples where the stress that we require in the member is more than the yield stress. So basically, you cannot solve it like that. So what I'm trying to say is that if you think of, elasticity, perfect plasticity is like this. If this stress that we calculated, it happens to be here, then it means we need to truncate it as at this yield stress, and we could not use basically this, this nice relationship here. So a stress-strain relationship here is based on the assumption of elasticity, okay? Because it's our linear assumption. Anyway, assuming that this is all elastic and it's good, then you just set these two numbers to be equal. So you would simply say, I don't know, 1.25p divided by pi over 4, 0.04 squared. That's the stress from the first equation is 156.25 megapascal, so 10 to the power 6. And from that, you can calculate P to be 157.08 kilonewtons. Okay? So you can just calculate it. You have now all the equations and unknowns that you require. Is that clear? Do you have any question? All right, so that was the third exercise. The fourth and the last exercise is the following. So we have a polymer block, and we apply a shear force on top of it using these solid surfaces. Okay, I need to mention this, that usually when we talk about polymers, they are usually nearly incompressible. So Poisson ratio is very close to 0.5. Okay, so usually when you want to do tests on polymers, we are interested in their shear modulus. And the test that you do is always a shear test, which looks like this. You know, this is kind of the opposite of what you have for steels or things like aluminum and stuff like that. For them, we usually know Poisson ratio is between, I don't know, 0.25 and 0.3. We are interested in E. And then for them, you usually have this sort of what we call dog bone samples, you know, the one that I also showed you. And for them, we apply tension test. Okay, so we usually have a shear test, we have a tension test. Shear test gives you G, it gives you shear modulus. Tension test, it gives you E, it gives you elastic modulus. Okay, so for some materials, E is the bigger question. For something like polymer, is usually G the question. And this is exactly the way you are going to, you know, test this. And sometimes there are these things that they are called rheometers. So basically, they take like a disc and they apply a shear via torsion to it. We also come to that. But anyway, the question is like this. So my point being that you should pay attention to the direction of the force. Okay, so what happens to this sample is that it becomes like this after you apply that force. Okay, now the shear strain here would be gamma, right? And what you want to do in this example is to compute shear modulus, again, G. Now, remember the relationship between G and gamma? Tau equals G gamma, right? So you can compute gamma from this little triangle. So this is geometrical. And you can compute tau from that force. This is basically shear force divided by area. Okay, so you compute the shear force divided by area, that would be shear stress. From the geometry, you compute shear strain, and then the coefficient between is the shear modulus that you are looking for. Okay, so let's say this thing deforms like that, and this angle is gamma. And the question, by the way, tells you that under this force, you get 2 millimeters. Okay, so this is 2 millimeters. So obviously gamma is, again, you can imagine gamma is small, so we do this assumption of sine equals theta and so on. So we would just approximate gamma by 2 divided by 200, basically. So 2 millimeters divided by 200 millimeters. So gamma is 0.01. That's shear strain. Now, shear stress, tau, is shear force divided by area. Shear force is the force that you apply up there. So this is your 2 kilonewton. Now, what is this area? You should think of it this way. You know, you apply that force on a plate, which, I mean, you don't see the third dimension in this picture. But, okay, let me sort of draw that. There is a third dimension into this picture, right? There is a surface here on which you apply the force. So that's where the force gets distributed on top of that surface, okay? So that's where you get your shear force, basically, all right? Now, the area of that rectangle, which is going inside the page, is 400 times 100. Okay, 100 is the width of the block in the third direction, which is not shown. Does that make sense? So you basically have, I don't know, you have a picture like this, if you think about it, and that shear force or shear stress is, let's say, distributed on top of that surface, which you don't see. And then they collectively would be equal to let's say, what you apply. All right, so area is 400 millimeters times 100 millimeters. And this gives you tau to be 50 kilopascal. Okay? Now, all you need to do is to basically use your relationship, tau equals G gamma, or otherwise G equals tau divided by gamma. Now, you have tau, 50 kilopascal, you have gamma, 0.01, so G is 5 megapascal. All right? Is that clear? Do you have any question? All right. That was the fourth and the last exercise for today. Thank you very much for your attention.